Can you still see my screen?
I see APA, yes.
Yep. Welcome everyone to the 2020 APEC Groundbreakers virtual tour by APEC OUC. This year, our event would be the biggest one ever done, with 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it would cover sessions in 4 different languages. Please remember to register for as many sessions as you can. All sessions will be available for replay as many times as you want for 2 weeks after the initial session date and time. You can also interact with the speaker at any time during those 2 weeks by posting questions or comments directly in the playback session page. I would like to say thanks to all Oracle user groups and Java user groups that made this event possible, and also to our sponsors, Oracle Groundbreakers and CloudDB. Now for today's session, how to figure out why your query is taking forever in less than 30 seconds by Kaley Crum. Please feel free to write questions at any time during the session using the Q&A tab of the Zoom webinar, and the speaker would be answering them at the end of the session. If you experience any issues during the presentation, please feel free to contact me at any time using the chat tab of the Zoom webinar. Now, without any more delays, I would like to leave you with this amazing session by Kaley Crum.
Awesome. Thank you so much. I appreciate you.
I'll just stop sharing, and if you can share your screen.
Yeah, let's see. Screen 1, share. Okay. You able to see the PowerPoint? Fantastic. Okay, so name of today's session is how to figure out why your query is taking forever in less than 30 seconds. My name's Kaley Crum, and we're going to have a lot of fun today. We've got 3 main points that I'd like to cover. Number 1, we're going to be talking about the different types of time for a query. Second thing we're going to be talking about is I'm going to be showing you my secret weapon. This is my secret weapon for anytime anybody comes up to me and says, Kaley, I've got a slow running query. Would you mind taking a look at it? And some of you might be thinking, oh, it's probably the execution plan of the query. Nope, it's better than the execution plan. And number 3, we're going to talk about patterns to look for with slow queries. So let's talk about different types of time for a query. Let's take a step back from the database world. Let's talk about you for just a second. At any point in time, you are either doing one of 2 things, right? You're either doing something, right? You're feeding your pets, you're grocery shopping, you're preparing a meal, you're ironing, you're exercising, you're doing all these various things. Or if you're not doing something, if you don't have an end goal in mind that you're working for, you're probably doing nothing. And if you're doing nothing, it's probably because you're waiting on something. For example, maybe you're sleeping, right? That's the paramount example where you have to wait essentially on your batteries to recharge. If you're not eating pizza, it's because you're waiting for the pizza delivery guy to arrive. If you're not on your way home from the supermarket, it's because you're waiting in the checkout line. You're waiting for the coffee to brew. You're waiting for inspiration to write that novel that you've always wanted to, whatever that means. You're waiting for your tax return money before you pull the trigger on that big screen TV. You're waiting in line at the post office. So at any point in time, you're either doing something or you're waiting. There's no third option. You're either doing something or waiting. You say, what the heck, Kaley? What has this got to do with anything about Oracle database? Well, we'll talk about that in just a second. By the way, waiting does not necessarily correlate with inefficiency, right? Your life is going to have some wait time that's going to be built into it. And that's okay. It's not like you can just skip the line at the grocery mart. You can't just make pizza appear instantly on your front doorstep. You're going to have some wait time. You don't want too much wait time. If you wait too long to write your novel, you're never going to get your novel written. You say, what the heck does anything of this have to do with Oracle database? Well, an Oracle server process is a lot like you. Because at any point in time, an Oracle server process is going to be doing one of 2 things. Either it's going to be doing something, meaning it's going to be executing code, meaning it's going to be burning CPU cycles, or the Oracle server process is going to be doing nothing. And if it's doing nothing, it's because it's waiting on something. And if it's waiting on something, it's not burning CPU. It's not burning through code cycles. It's simply sitting there with its arms folded, taking a siesta. When an Oracle server process is executing code, we say that it's on the CPU. And whenever an Oracle server process is waiting, we call it a wait event. Now, why on earth would Oracle need to wait? The answer is there are literally thousands of reasons that might cause Oracle to have to wait for one reason or another. And it wouldn't make a very fun or interesting presentation to go through all of them, but I'll just cover some of the highlights, right? One example might be if Oracle is waiting off of a block to be read off of disk and into the database's buffer cache. Oracle might issue a read request, and the operating system says, got it, I'll take your read request and I'll let you know whenever that read request is complete. Oracle's just going to go, okay, thanks, appreciate that. And Oracle can just say, wake me up whenever I get that block loaded into the cache. Another example might be if we're waiting on a row level lock on a table. If we're maybe updating a table and we come up to a row that's locked, we're not going to be able to do anything because of that lock. So Oracle just kind of puts itself to sleep. Another example is if maybe we're trying to jam some extra data into the log buffer, but log buffer is full. We're waiting on the log writer to write the log buffer so that we can keep writing redo entries. Maybe we're waiting on the database writer to write dirty buffers to disk in order to make space for a free buffer that we can load into the buffer cache. Or maybe we've got a distributed query that's got half on a remote side of a database link and half of it on the local side of the database link, and we've got to wait on stuff to happen on the remote side before we can do anything with a result set. Maybe we're trying to pin a cursor that everybody else is trying to pin at the same time, and as a result, Oracle kind of throws a little bit of a back off algorithm where we don't try to crowd it. And Oracle says, let me just wait for a minute and see if any of the contention clears up. Maybe we're waiting on a query to be issued. Maybe we're trying to gain an exclusive lock on a table before changing its definition. Maybe we're trying to get a block off the interconnect and rack. So there's thousands of reasons for these wait events. And by the way, whenever you and I think about a wait event in our own human lives, we tend to think about waiting in line at the grocery market, at the supermarket, maybe for 10 minutes, or maybe we're waiting 30 minutes for the pizza guy to show up, or maybe we're waiting 5 minutes for coffee to brew. Whenever Oracle experiences a wait event, usually they're extremely short-lived. Oracle can switch back and forth between CPU and wait event hundreds or even thousands of times in a second. And anytime you have a long-running query, some of that time is going to be spent probably on the CPU, and some of it's going to be spent probably waiting. Most healthy long-running queries are going to have some kind of mixture. And by the way, having some wait time is not necessarily bad, in the same way that your regular lifetime is going to have some wait time associated with it. Oracle server processes really aren't that different. They're going to have some wait time usually associated with those as well. So the main thing that I want you to take away from part one is at any point in time when you're running a query, Oracle's either waiting or it's on the CPU. There's no third option. It's either waiting or it's on the CPU. Okay. With that in mind, I'm going to show you my secret weapon for attacking any SQL tuning situation. Anytime somebody comes to me and says, Kaley, I've got a slow running query. Would you mind taking a look at it? This is the very first thing that I ask for. And it is a SQL monitoring report. So this is what a SQL monitoring report is. You might be asking, well, how do you get a SQL monitor report? Well, I'll show you the long way. What you do is you run a query that selects from Dual, and it uses the DBMS SQL tune package, the report.SQL monitor report SQL monitor procedure. What you do is you pass in enough information to uniquely identify the query that you're trying to get a report for. So if you're the only session in the database that has this particular SQL ID, you can just pass in a SQL ID. If you're the only person on this instance that's running the SQL ID, you can do a SQL ID and an instance ID. Or maybe we can uniquely identify just what the session is running by giving us an instance ID and a session number and a serial number. Or maybe we're running multiple statements and we have to specify all 4 of these. So you can pass in as much or as little information as you want, and Oracle will try to narrow it down as best as it can to the query that meets all the criteria. Additionally, you specify your type of report. I prefer the HTML reports just because they're going to offer a little bit more information, and they're a little easier on the eyes than a plain text report, but they're not as big and bulky and other issues that you might see with a Flash report. And then there's a detail level that you can express. What this does, if you run this query, you're going to get back a series of HTML pieces here. And what you have to do is you have to take all this HTML, you have to select it all, then you have to copy it using Control-C, then you have to go to your desktop and you have to create a new text document, then you've got to give it a name, and you got to open it, you got to paste it, then you got to save it, and then you've got to close out of your notepad, and then you got to right click and rename, and you got to give it the .html extension. And then suddenly when you do that, you're going to end up with a SQL monitoring report. That's the most difficult way to go about it. I'm going to show you a super easy way that kicks the living crap out of this method at the end, if you hang with me to the end. But the first thing that I want you to notice is that there are 2 columns here. There's a CPU activity column and there's a wait activity column. Hey, now wait a second. That sounds familiar because just a second ago we were talking about CPU activity and wait activity, or we talked about CPU and wait events. So this is essentially the same thing. One of the things that you should know is that Oracle tries to make this column sum to 100%. And it tries to make this column sum to 100% as well. You can see that we've got 98 and then 1.9%. Well, we're missing 0.1% somewhere, but this is based off of sampling. So this may or may not be totally 100% correct. Here, we're missing an entire percent because this is 98 and this is 1. So it doesn't quite sum up to 100% over here. But the general idea is that the columns roughly sum to 100%. Okay. So here we figured out we're spending 98% of our query CPU time on this step. And we figured out that we're spending 98% of our query's wait time on this step. And if those are our only 2 options, CPU activity and wait activity, if we're spending 98% of both of those options here, then clearly that's our bottleneck. This sixth step right here is going to be our query's bottleneck. It's going to be the step that we're spending the most time on. Okay, so again, we have to remember that we know that we're either waiting or we're burning CPU, and that there's no third option here. But let me ask a question. Let me show you a different SQL Monitor report. Here we've got 100% of our CPU activity on this step. And here we've got 100% of our wait activity on a different step. So the question is, what's more important here? Should we pay attention to wait activity time or should we pay attention to CPU activity time? First thing that I want you to know is, and the big thing is, why do we care about either CPU or wait activity? First thing I want you to know is that for this query, we actually care about CPU. You might actually be tempted to think, oh, well, why should I focus on CPU? Well, in this case, there's a specific reason why you should focus on CPU. The main reason we want to focus on the CPU is because if we look at the database time for this query, you can see that we have a green bar that stretches all the way across. And this green bar indicates that CPU activity is being burned. In fact, you can actually mouse over this bar and Oracle will pop up a little tooltip that says CPU 106.09. So Oracle's saying you've spent 107 seconds on database time approximately, and 106 of those have been spent on the CPU. That's 98% of your database time. So think about it. If we were to approach this situation and say, I actually want to tune all the wait time out of this, you'd be removing about 1 to 2% of our query's runtime. You'd be removing about 1 second out of 107 seconds of our wait time. So that's why we actually want to focus on CPU here. Our biggest tuning opportunity is anytime we have big chunks of time on something. So if we have a query that's CPU intensive, we want to focus on CPU. If we have a query that's based on a lot of wait time, we want to focus on the wait time. So we just want to focus wherever the big chunks of time are. So it makes sense to focus on your execution plan steps that make the most time. Once we've identified where our long-running steps are, then we can go about trying to figure out methods that are going to prevent us from. We can go about figuring out methods that are going to shorten our query's runtime. Okay, so we talked about the different types of time for a SQL. We talked about how there's CPU time and wait time. We've talked about the SQL Monitor Report. Now I'm going to tell you basically how to read the SQL Monitor Report, or patterns to look for. So basically, the first thing that we want to do is you want to check out this bar at the top right here. This kind of serves as the key to reading the rest of the report. Here we can see that we spent 8,201 seconds of database time on this query. So that's quite a while. We can tell that this query has already been running for quite some time. And we can see that there's this huge green bar of CPU. And again, if we mouse over it, Oracle tells us the exact values for how long we've been running this query and what percentage of our time that is. So we can tell that 96% of our time's going on the CPU. And if we mouse over this tiny little bar right here, Oracle tells us that 260 seconds of our query is made of wait time. We can actually look at the visuals at the size of this bar, and we can see that, hey, here's all this green, and here's this tiny sliver of, well, it's not green. And we can actually deduce from that Oracle's drawn these to scale and that this query is extremely CPU intensive. So we can just kind of glance at this bar and know that we've got a CPU intensive query. And so what we should do is we should come down to our CPU activity column, and we should look for our most CPU intensive step. Okay, well, that's not hard to find right here, because you can see where 99% of our CPU activity is actually being spent on step 6 here. So we know that at the time of this that this report was being generated, that table B is where we were spending the majority of our time. Table B was our query bottleneck. Okay. Why do we think that is? Well, let's go ahead and try to figure out what's going on within this execution plan. So the first step that we're looking at is a full table scan on table A. And this is scanning right now. We've pulled up 15,905 rows. Each of those 15,905 rows get bubbled up the execution plan until they eventually get past this filter step. This filter step has two different children here. We've got a partition range single, and we've got a table axis full. Both of these are direct children of our filter step that we can see here because of the way that they're indented. So what happens here is you'll notice that we've got 15,905 rows that have bubbled up, and this table scan has been invoked 15,906 times. So what's going on here? This is actually just a slight delay that's caused by just taking this snapshot at the exact wrong moment in time, essentially. But what's going on here is for every row that we get from this table, we bubble it up and we invoke this filter operation. And this filter operation scans our table over and over and over again. So what's happening is 15,000 times we bubbled up records and we've done full table scans. So we've literally done full table scans on table B for 15,906 different times. So that's why we're spending all of our time on this particular step, is because we're just scanning table B here over and over and over again. We could actually figure out basically how long we're spending on this step, right? So you can see that 99% of our CPU activity is being spent on this step. And we can tell that out of the 8,200 seconds here, that we've spent 9,000 or 7,940 seconds. So if we take 7,940 seconds and we multiply it by 0.99, because that's going to be our percentage, we can tell that, by the way, we would have to normally add in the wait time here. But if we look at this wait time here, we can see that it's actually nothing. So this is entirely about CPU. If we do all the math out, we can see that we've got 7,940 seconds. We multiply that times 0.99 to account for this percentage. And we're spending a total of 7,800 seconds scanning table B. All right, let's try another example here. Here we've got database time. We spent 521 seconds on it. And so if we were to math that out, that's going to be about 8 minutes and 41 seconds. But we could just look at this database bar and we can kind of go, okay, it's made of about 2/3 CPU and maybe 1/3 wait time. So we're looking for a step that's probably going to have more CPU than wait time. We should put more emphasis on CPU time, but maybe we're looking for a step that includes some wait time as well. So when we take that into account, we start scanning down through this bar, looking for our most time-intensive step. And hey, we found it. This step right here, we're spending about half of this green bar on this step right here. And we're spending almost the entire pink bar on this step right here. So about 2/3 of our query time is being spent on this hash join. Okay, why are we spending so much time on this hash join? Well, let's take a closer look. One of the things that we can see is that we have a bunch of physical I/O going on with this hash join. Well, that's unusual. Usually in a hash join, you don't have physical I/O associated with a hash join. Usually the only time you would have physical I/O associated with a hash join step is if your hash join doesn't fit into memory. And so you're having to write out part of the records that you're joining to disk as a result of writing it to temp. And you can see that that's actually what's happened here. If we look at memory, you can see that we've used a significant amount of memory from our PGA, and we've also written out 36 gigabytes of temp space. So we are basically performing all of our time doing physical I/O as a result of, or a significant portion of our time doing physical I/O as a result of a hash join that won't fit in memory. Why won't our hash join fit in memory? Well, because we're trying to hash up 273 million records. Okay, well, why do we have 273 million records that we're trying to hash up? Because if you look at the step before that, before we only had 7,466 records. Somehow it jumped to 273 million. It changed several orders of magnitude just from jumping to one step in the next. The answer is we actually have a merge join Cartesian over here. If you take 7,466 and you multiply it by 36,525, you end up with approximately 273 million. So as a result of a merge join Cartesian, this hash join is just getting flooded with more records than it knows how to handle. And as a result, it's having to write part of its hash buckets out to memory. Partitions, I guess is the right word. So it's having to write the partitions from the hash join out to memory. So all that to say that this step 4 is where we spent most of our time. But this was not the actual problem of the query. This is actually just a byproduct of the actual problem of the query. The actual problem of the query was this merge join Cartesian, where Oracle thought we were only going to get one row back, but we actually ended up getting 273 million rows back. If we would have gotten just one row back, that would have been fine, right? We could have taken 36,525 down here and just multiplied it by 1, but we didn't multiply it by 1. We ended up multiplying it by a lot more than that. So know that whenever you see a step where you're spending the most time, that may not be the actual problem itself. It could just be a symptom of the problem. Okay, let me show you another one here. We've got database time, and the database time for this query is 288 seconds. Again, you can look at the database time here just visually and sort of indicate that, okay, this is about 1/3 CPU and about 2/3 wait time. So we should look at physical I/O here because of this pink salmon-y color. That's what's going to indicate it's actually physical I/O. Although going back, any color other than green is going to represent a wait event. So this is going to be one kind of wait event, and this is going to be a different class of wait event. Okay, if we go down here, sorry, I keep bouncing up. We see where this is, the majority of this is being handled by wait events, right? So we want to look for our most wait event intensive step. Well, there's kind of two options where it could be here. It could be this one. We're not spending as much time on the wait event, but we are spending quite a bit of time on CPU, whereas this is spending a significant amount of time on wait event, but it's spending very little on CPU. So we had kind of a mix. It could be either one of these. So we just kind of want to compare this to the database time bar, and we want to figure out approximately how much time we're spending on each of the steps. So for this first step here, right here, you can see that we are spending 35% of our time on the CPU bar here. So if you were to picture taking this green CPU bar and cutting it down to about a third of it's going on this query right here. And about 4.5% is being spent on the wait activity. So if you could imagine a slice about this big, that's what I'm estimating to be about 1/20th of the wait time here. That actually might be a little bit large for 1/20th. Versus down here, if you think about 8.9% of the CPU time, okay, if you were to cut this in 10, then 1/10 would be about that much. Versus 82%, that's going to be about 4/5. So if you were to take this bar right here, this pink and this blue, that represents our wait time, and do about 4/5 of that bar, you'd probably come up with this much time. So you can see where this is a significantly larger period of time than what we had earlier. This is going to be a much smaller period of time right here. So this is our clear bottleneck right here. This is the step that we need to focus on, is this index full scan. A few things to notice here. Number one, we're getting 103 million rows through an index full scan. That's kind of unusual. I'm not sure why Oracle would ever want to get 103 million records out of an index full scan unless you just have a huge table. But we'll get to that here in a minute. Something else I want to talk about is these colors over here on the left-hand side. You see we've got a little pink, we've got a little green, we've got a little blue. These colors actually correspond to something. Just keep those colors in mind for a second. Also notice that our longest running step is in this red here. All right, go back up a little bit. Let's have a look at the parallel execution details. You can see that we actually have 3 different colors right here. We've got our pink, blue, and green. And the pink is our query coordinator, and parallel server set 1 is green, and parallel server set 2 is blue. And basically everything that you saw that was pink was being performed by the query coordinator. Everything that you saw that was green was performed by the parallel server set 1, and everything that you saw that was blue was being performed by parallel server set 2. And remember that we said that the longest running step was red. What that means is it's getting run by the query coordinator, and anything that is run by the query coordinator is not going to be parallelized. So we have a parallel query here. We've got our query coordinator, and we've got all of our parallel servers that are executing. you can see where we're spending the majority of our time right here on the query coordinator. That's exactly what you don't want for a parallel query. You actually want the opposite of that. You want your query coordinator to be doing very little of the work, and then you want your parallel server sets to be doing the majority of the work. The reason behind that is because these guys are going to be able to parallelize it a little bit more versus this guy who's going to be working solo. So this is a pretty good indication. When you see this huge amount of time being dedicated to the query coordinator and very little time being dedicated to the parallel server sets, you can see that this is a pretty good indicator that we have an extremely unhealthy query. This would be an example of an extremely healthy query where we've got almost nothing being done by the query coordinator and lots of stuff being done by the two parallel server sets, but that's not what we're dealing with. This is the unhappy reality here. Is we've got a parallel query, but almost nothing's being done in parallel so far. Also, you can notice that we've done about 288 seconds worth of database time, and the query coordinator has done 219 of those total seconds. So the question is, why is it not being parallelized? Well, if we look at the plan, we see that it's an index full scan. Anytime you have an index full scan, or really anything that anytime you have a full scan on a non-partitioned index, you're not going to be able to parallelize it. Now, why did Oracle choose an index full scan? I'm not really sure on this one. I don't have the text to this report, but it could be a case where either I would think it would be something like somebody using a hint to force an index or something like that. I would think that this would be probably pretty unusual in most cases. But moving on, we'll go to another scenario here. Suppose we've got this table. We've spent 24 seconds, so not very much time at all. Majority of the time appears to be on wait time. So what we would do is we'd go down and we would look for our most wait-intensive steps. Well, you can see our most wait-intensive steps are right here. And you can see that the majority of time that we're spending is actually I/O time. And of those 24 seconds that we've spent, we've got about 45 of them being dedicated to this step right here. And actually, it's both of these steps. You can see that table E and index E are probably working together. But you can see, okay, you might be saying, okay, why are we spending so much time on wait events? It's because we're spending so much time on physical I/O. Another one of the columns that a monitor report exposes to us is the number of physical I/O read requests. So you can see here that we've done 2,184 physical read requests, and the step above it has also done is responsible for another 20% of those physical I/O read requests. And again, we're having to do 2,243 physical I/O read requests. So the combination of these two steps right here add up for about 65% of our query's total wait time. So what are solutions we could do? Well, we could look at a way to get table E and index E into buffer cache somehow to prevent us from having to do that physical I/O. Or maybe we could read table E and index E less or fewer times. Maybe we could come up with a more selective index, or maybe we could come up with a better join order that's going to cause us to filter out records before we touch table E and index E. Maybe we could use other caching mechanisms, such as a result cache or in memory. Maybe we could get faster hard drives. Maybe we could balance the work between multiple hard drives if we have ASM. So there's lots of possible solutions here, you can see. Let's go on to the next scenario here. We've got database time. You can see we're all about CPU time. It's easy to find our bottleneck. Right here is where we're spending the majority of our CPU, and the query is almost entirely about CPU. So this query, our bottleneck so far, within the first 26 seconds of it, is a full table scan. right here on table A. So things we might want to look at is, can we use indexes on this table rather than doing a full table scan? Or maybe we could use parallelism to do a full table scan. Maybe if table A is a sufficiently large table, maybe it needs to be shrunk, right? Maybe we can do an alter table move if it's got a bunch of empty space in it. Maybe we could apply compression. Maybe we could create a table that's actually just a very narrow version of the table that omits any records that we don't need. And that's so that we can make our rows shorter. And if our rows are shorter, we can fit more rows in a block. And if we can fit more rows in a block, then our table occupies fewer blocks. And if our table occupies fewer blocks, we have to scan fewer blocks whenever we're doing a full table scan. Therefore, by scanning less data, our query runs faster. Or we were already using partitioning, but we could look at using subpartitioning. Another example might be if we're on Exadata, maybe we could do an Exadata zone map. So there's all kinds of solutions. Let's try and have a whack at this one. You can see from the database time, this one's been running for a while. It's about 1,500 seconds. And again, if we look at the database time, you can see everything's being done by the query coordinator. Virtually nothing is being parallelized. So we don't really even have a parallel query here. It's all just being done by the query coordinator. If we look, it's all about wait activity. Where's all the wait activity going? Well, it's this load as select step. So this means that we're doing a direct path step. Now, something interesting to note is that this is being done by the query coordinator. And the real issue is that our select down here is being done in parallel, as you can see. So the insertion is being done in serial, but the select is being done in parallel. What does that usually mean? Well, usually it means somebody forgot to do an alter session enable parallel DML. If you're doing a direct path insert and you're doing the select in parallel, usually you want the insert to be in parallel as well. Here's another example. We've got a database time of 707 seconds, all being done by the query coordinator. Absolutely nothing being done by any of the parallel workers. We scroll down. We're looking for the most CPU intensive steps, and we can correlate that with our bitmap index single value here. Now, that's not a perfect alignment, but you can see that when we do scan this bitmap index, that it actually gives us 346 million records. And then we go and we touch the table 346 million times up to, and we end up only coming back with about 10,000 records. So really, this looks like it might be a selective index, but we've actually only been able to filter out a significant amount of the rows after we've done touches on the table. So what are solutions here? Well, maybe instead of a bitmap index, we need to look at doing a full table scan. Maybe we need to take our full table scan and make it run in parallel. Here's another scenario where this query is actually errored out. It says we apparently ran out of temp space running this. If we go down and we look at the, well, going back up, database time says it was mostly CPU. So if we go to look downward, we're looking for our most CPU intensive steps. And you can see that they're all right here. They're all grouped right here. Well, what happened to cause all these steps to suddenly become CPU intensive? If you look at the number of rows returned from each of these operations, we start at 840, 848, 4840. Then we jump up to 78,000. Okay, that's a lot. Then we go to 485,000. Okay, that's a lot. That's a lot. And then we skip clear over the millions and head straight to the billions. We say 2 billion, 2 billion, 2 billion, going all the way up here, right here. So suddenly we've just taken a turn for the absolute worst, and our result sets are just huge right here in the middle. So what can we do to troubleshoot this scenario? Well, one thing is Oracle's possibly picked a bad join order. And this could be due to a number of things, such as stale statistics or missing histograms or missing column groups or whatever. There could be a scenario where we have missing join criteria between multiple tables. So you can see where this is hugely valuable. I remember being on the phone once with a lady, and the lady said, "Kaley, SQL tuning just scares the living heck out of me. It puts the fear of God in me. I think I'm going to, keep thinking that somebody's going to bring me this massive execution plan, and I'm not going to be able to understand it." The thing is about these SQL monitoring reports is they allow you to put your focus and emphasis on the steps where you're spending the most time. And so I'm going to show you how fast that you can actually make this. This is the super fast diagnostics technique. You just look at the time bar. You see if you're either CPU heavy, meaning if you've got lots of green, or if you're wait time heavy, meaning you have lots of non-green. And then you just find the step where you're spending the most time. So let me just show you, and then you can look for clues in this low row. So things like, are you processing large numbers of records? Are you doing lots of physical I/O? Are operations spilling over to disk? Or do you have maybe you don't have the partition pruning that you thought you were getting? Maybe your operation's not being parallelized. And so you start looking for these clues. And if you can't find anything, you just look at the steps that are leading up to your slow row. Okay, so here we've got a step that's table access by local row ID, and you can see where we're spending a significant amount of CPU, but we don't have all that many records. So why are we spending so much CPU here? Well, the answer is the step before. It says we're doing a bitmap conversion to row IDs here, and we're trying to use 3 billion records to do table access by index row ID. That's almost always going to be an awful idea. So caveats to this are you want to make sure that you're doing you want to make sure that you have the tuning and diagnostic pack for this. You want to make sure that you have something else that you want to be aware of is your most time intensive step can actually change over time. As an example, you might have a query that runs for an hour, and maybe it takes 5 minutes to scan table A, and then it takes 55 minutes to scan table B. And if you're doing a hash join between the two, then you're going to scan table A first, and then you're going to scan table B second, right? So you're going to spend 5 minutes scanning table A, and then you're going to end up scanning 55 minutes for table B. All right. So if you were to take a SQL monitoring snapshot right here, about 5 minutes in, it's going to look like you're spending all your time on table A, when in reality, you've just not allowed ample time for your bottlenecks to unfold. You would have to take a snapshot right here, somewhere beyond this point, before you start to realize that table B is going to be your query's bottleneck. So you want to allow ample time to allow your query bottlenecks to unfold. Okay. Something else to keep in mind is that a SQL Monitor report is not going to generate if you have an execution plan that's too long. If you have over 300 lines, there are ways around that, and I'll let you Google for those. Parallel queries and DDL will create a SQL monitoring report immediately, but if you have a query that's not DDL and it's not a parallel query, then you have to let your query run for at least 6 seconds of database time before a SQL monitoring report will actually generate. So you basically want to be able to find your session quickly, and then you want to be able to spy on your session. You would do that by running a query like this that joins $session and $SQL. And from there, you would write a script that does the work of creating that HTML file for you and automatically opens it for your SQL window. And I've actually shown you how fast you can go about doing that. If you pull up a copy of SQL Developer and you have a script that identifies sessions of yours, you can use that to quickly identify your SQL ID, your session ID, all that information. And then you can just pass that into another script where you can go and it will automatically create and do all those steps that I mentioned earlier, create those SQL monitoring reports where you can go pop it open and you can scroll down and you can quickly identify where your query's bottleneck is. And you can see, hey, we're spending 96% of our CPU here because we're processing 4 billion rows. This video was taking real time. You can see I wasn't like typing at a breakneck pace. So this is a significant thing that I wanted to give you guys. Basically, you could go out, you could write these scripts that'll do it for you. But I just wanted to give them to you today as my sort of thank you for hanging out with me as far as attending this presentation and stuff. So you can go download the scripts that will create the SQL Monitor reports and identify your sessions at tuningsql.com/forever. Are there any questions or comments that I'm saying in the job? We see. Do you have a job that collects long-running queries and sends the email SQL monitoring report automatically, please? I don't have a job. I've got those 2 scripts, and those 2 scripts will automatically. I mean, as long as you're typing those in. But I mean, I suppose you could do a job that automatically takes the SQL or the HTML that automatically archives them off into a table using a clob or something. So no, I don't have a job, but yeah, if there are no other questions, I guess I will hand the reins back over to our host here.
Thank you everyone for participation today, and please do not forget to register for another great session in the conference and to interact with the speakers in their playback session page. Please enjoy the rest of the conference.
Awesome, thank you.
Thank you.